Hello again. Today we're going to be talking about the definition of the derivative. It's going to incorporate stuff that we've talked about previously, and the derivative is one of the most important things in calculus, along with the integral. It's your two basic tools that we're going to be using all throughout the course. Anyway, so as we've talked about previously, this is the equation of the slope of the secant line, specifically between the 2 points x equals x and x equals a. Now that we've learned about the limit, we can define that the slope of the tangent line is going to be the limit as x approaches a of the slope of the secant line. Okay, as we've talked about previously, if we bring the 2 points at x equals x and x equals a, if we bring them closer and closer together, our slope of our secant line should approach the slope of the tangent line, and that concept is exactly what the limit does. It evaluates what this function does as x gets really, really close to a. So this is how we're going to define the slope of the tangent line. Now, the derivative of a function at x equals a is denoted like this, f prime of a. This little prime symbol is the derivative. So this specifically is the first derivative of our function at a. If you wanted to talk about the second derivative, it would look like that with two little primes. I'll talk more about the notation later, but for now, this means it's the first derivative of our function at a, and as you see, it's defined to be exactly the slope of the tangent line at a. Okay. So let's go ahead and use this definition in a couple of examples showing you how to calculate the derivative of a function at a using this definition. Okay, so I'm just going to pick an example off the top of my head. Let's say that we have the function f of x equals x squared, and we're trying to compute the derivative of our function at 1, which is the same thing as saying find the slope of the tangent line at a equals 1. Okay? Okay, so I'm just going to straight up use our definition. In fact, I'll write the definition first. The derivative of our function a is the limit as x approaches a of f of x minus f of a over x minus a. Okay? Then using our definition of our function, which is x squared, f of x becomes x squared and f of a becomes a squared. So we have the limit as x approaches a of x squared minus a squared over x minus a. Oh, we're doing the derivative at 1, so I should really replace all of these a's with 1's. Okay, so let me erase this, go back one step. So this was the definition. Now let's plug in 1 into our definition. So the derivative at 1 is the limit as x approaches 1 of f of x minus f of 1 over x minus 1. Okay. Next, use the definition of f of x so that that becomes x squared and that becomes 1 squared, which is simply the number 1. Okay. Now we just do the limit of this. If we try to plug in the number 1, we get 0 over 0, which is indeterminate, which means we have to simplify it. Well, the top can be factored into x minus 1 times x plus 1. Then you can cancel an x plus 1 on the top and bottom. So this becomes the limit as x approaches 1 of x minus 1 times x plus 1. The x minus 1's cancel, just leaving the limit as x approaches 1 of x plus 1. So you plug in 1 because that's just a polynomial and you get 2. So we've just shown that the derivative of our function at 1 is 2, which is the same thing as saying the slope of the tangent line at x equals 1 is 2. Okay? So there's a couple of different ways they can word a problem where you're basically doing the same thing. If they ask you for the slope of the tangent line, or if they ask you for the derivative, either way, you're going to be using this equation, at least for now, until we get to our derivative rules. We will be getting to those shortly, and they'll give us a way to do this without having to use the definition of the derivative. But you really should know the definition of the derivative, especially because in your homework problems, they're going to throw you problems where maybe they'll ask you to simplify something of this structure. You know, they may not be saying that you're computing part of the definition of the derivative, but they just throw the equation at you and say to simplify it. And really the equation comes from this. And so they're really sort of testing you over this sort of structure. You do need to know it, you know, even if you know your shortcut derivative rules. Okay, let's do another example. So what if our function is square root of x, and I want to find the, well, let me say, instead of finding the derivative at x equals 4, let's find the equation of the tangent line at x equals 4. Okay, so to get an equation of a line, we need two pieces of information usually. We need a point that's on our line, and we need to know the slope of the line. Okay, well, we know when x is 4, if you plug that in, square root of 4 is 2, and so f of 4 is 2, and therefore the coordinate point 4, 2 is a point on the tangent line. Now we just need to get the slope of the tangent line, which is exactly the same as the definition of the derivative. So using the definition of the derivative, our slope of our tangent line is the limit as x approaches a of f of x minus f of a over x minus a. Now in our example, we want a to be 4, so let's replace a with 4, like that. And then using our function f of x is square root of x, so this becomes square root of x, and this becomes square root of 4. Now, of course, square root of 4 is just 2, so let's just change that to a 2. Okay, once again, try to plug in your number 4. We wind up with 0 over 0, which is going to happen every single time. It's the way that the definition of the derivative is sort of set up, that you're always going to have a 0 over 0 indeterminate case. So you're always going to have to use some sort of simplification technique before you can evaluate your limit. You'll never just be able to plug in the number and be done, because you're always going to get 0 over 0. Okay, so to continue, this involves a square root, so we have to use the conjugate in order to simplify this expression. The conjugate of square root of x minus 2 is square root of x plus 2, and so you need to multiply by that on the top and the bottom of your fraction. Okay, and then something times its own conjugate is going to simplify nicely, so multiply those two things together, and without going through all the details, foiling it, you get x minus 4. Which is exactly one of our factors in our denominator. And again, I mentioned this before, don't multiply this conjugate out by this term because it's not designed to simplify nicely. Only the top is. So only multiply the top together, leave the bottom factored, then you can cancel off at x minus 4 on the top and bottom, leaving 1 over square root of x plus 2. So we now have the limit as x approaches 4 of 1 over square root of x plus 2. Now if you plug in 4 into that, you get square root of 4, which is 2, and then plus another 2, which is 4, so 1/4. Now we're not done with this problem because the original problem was to state the equation of the tangent line. We've got a point on the tangent line, and now we know the slope of the tangent line is 1/4. We can now put that together into the point slope equation of a line to get the equation of the line. Okay, so to continue, let me just write this information up here. I want my slope to be 1/4, and I want it to pass through the point 4, 2, and then we're going to be plugging that into the point slope equation of a line, which you should remember from high school, but here is the formula for the point slope equation. Y minus y1 equals m times x minus x1, where m is your slope, and the x1 comma y1 is some point that is on your line. So plugging this information into the equation gives us y minus 2 equals 1/4 times parentheses x minus 4. Okay. Distributing on the right side gives you 1/4 x minus 1. And then finally adding 2 to both sides gives us the equation y equals 1/4 x plus 1. Okay. So that should be the slope of the tangent line to the curve y equals square root of x at x equals 4. Okay. Maybe let's sketch the graph real quick just to verify that this all makes sense. Okay. So this is going to be a quick rough sketch of the graph, but it should illustrate my point. Okay, 1, 2, 3, 4, 1, 2, and the square root function passes through 1, 1, 0, 0. It also passes through 5, 6, 7, 8, 9, 3, like that. And so this is a rough graph of y equals square root of x. Okay. Now let's graph y equals 1/4 x plus 1. Well, it has a y-intercept of 1, so that's right there. And it has a slope of 1/4. So if you go up 1 and right 4, that is exactly that point right there on our curve. If you go up 1 and right 4 more, that would be a little bit above the curve over there. And so if you draw a line through all 3 of those points, it certainly does look like it only touches it there on the curve, and therefore it's a tangent line to the curve at x equals 4. Okay, so this was the correct answer. Okay, one last thing I want to leave you with before we stop, but is that there's an alternate way to define the definition of the derivative. Okay, so instead of doing f of x minus f of a over x minus a, you can instead do this: f of a plus h minus f of a all over h, and then do a limit as h approaches 0. So this is an alternate way to define the definition of the derivative at a. Okay. So one advantage I see of using this over the other equation is that the denominator is a single variable h, which is certainly a lot nicer than the other equation where you have an x minus a in your denominator. See, when you use the other formula, you always have an x minus a in your denominator. You're always going to have to factor out an x minus a out of your numerator to get something to cancel. And sometimes factoring out that x minus a might be a little bit tricky. Here, we just have a single thing in our denominator, h, and so we'll only have to factor an h out of the top. It's a lot easier to factor out an h than to factor out an x minus a. Now, the one drawback of this equation is that some people have trouble expressing this part of the equation, what f of a plus h is, okay? Which is going to be your function, and you're replacing every x with a plus h, and then simplifying, okay? Let's really quickly do one example using this definition of the derivative, and then we're going to call it a day. So let's say that we have our function is, okay, I've already done x squared. Oh, let's say 1 over x. I haven't done one that is a fraction yet. And let's say we're trying to compute the derivative at 1, okay? And this time we're going to use this definition of the derivative, okay? So since I'm trying to do the derivative at 1, then a is 1. So this equation becomes the limit as h approaches 0 of f of 1 plus h minus f of 1 all over h, okay? Now, using our definition of f of 1 plus h is what you get when you plug 1 plus h in for x. So you have 1 over 1 plus h. And then minus f of 1, and if you plug in 1, you just get 1. So minus 1, and then all over h. Okay? Now we have a fraction on top of the main fraction, and this is another thing we've talked about previously in simplifying limits. And in this type of limit, you want to multiply by your least common denominator of all of your little denominators. Well, we only have one little denominator, that's the 1 plus h. So I'm going to multiply by 1 plus h on the top and bottom of this, okay? Well, 1 over 1 plus h times 1 plus h is just going to simplify to be 1, okay? And then minus 1 times 1 plus h, so that's just going to be minus parentheses 1 plus h. So I'll distribute that in the next step, so I'm not doing too many steps at once, okay? The denominator, just leave factored as h times 1 plus h. Now, you don't want to be in a hurry. These 1 plus h's don't cancel because this 1 plus h is a factor. It's multiplied by the rest, but this 1 plus h is being subtracted. And you can't cancel things that aren't factors, okay? You need to distribute the top first. Distributing the minus gives you minus 1 and then minus h. The 1 and the minus 1 is going to cancel, just leaving minus h, okay? So let's continue this up here. We now have the limit as h approaches 0, minus h over h times 1 plus h, okay? Now you can divide by h on the top and bottom. And now we're ready to plug in 0. If you plug in 0 for h, you get minus 1 over 1, which simplifies to be minus 1. So the derivative of f at 1 was minus 1. Okay, so we have two different ways or two different equations that we could use to define the derivative. There are some even other alternate ways to define the derivative. And I think I'll talk about that next time and maybe do some more examples. But I wanted this video not to be that long, just a quick introduction into the definition of the derivative, which is just the slope of the tangent line at the point. So a problem that asks you to find the slope of the tangent line, or a problem that asks you to find the definition of the derivative at a, is really the same type of problem. And for now, we just have to use this definition of the derivative to calculate. Okay, so that's a good place to stop. Hope I'll see you later. Have a good day.